All right, guys, let's talk about lesson 4, which is calculating heat of phase changes. So where can you use Q equals mc delta T on a heating curve, which is what this is? You can only use it on the straight solid, liquid, and gas lines only, so where the temperature changes, because you have that delta T component, that change in temperature. On the plateau pieces, the flat pieces, you're either going to use heat of fusion or heat of vaporization in order to figure out what the heat is needed for that phase change to happen. So when you're talking about heat of fusion, that is the heat needed to change a substance from a solid to a liquid or from a liquid to a solid. So you're going to need the heat of fusion constant for water, which is in table B on your reference packet, and you're going to use the heat of fusion equation, which is on table T in your reference packet. Heat of vaporization is what you're going to use when a substance goes from a liquid to a gas or from a gas to a liquid. And again, that constant is on table B in your reference packet, and the equation for it is in table T. So what is going to affect the heat of fusion or heat of vaporization? Well, that's going to be strictly based on the fact that it has either strong intermolecular forces or weak intermolecular forces. If the compound that you're talking about has strong intermolecular forces, then it's going to have high heats of vaporization and high heats of fusion due to the fact that it has high melting and boiling points. It needs a lot of energy, a lot of heat to get those molecules to move away from each other. So let's look at a couple examples. Let's look at a heat of fusion example first. So it says, how many joules does it take to melt a 16-gram sample of water at 0 degrees Celsius? Since it's at 0 degrees Celsius and that's the melting point of water, you know it's going to be heat of fusion. If you don't know that, that's something that you need to practice and you need to get your brain trained to identify. So the first thing in any kind of these math problems that we need to do is we need to list the variables that we're given. So we don't know what Q is because that's what we're solving for. We know what the mass is, and since it's a heat of fusion problem, we need the heat of fusion constant from table B in your reference packet. So then we're going to plug everything into the formula and then solve. And remember, this has 2 sig figs, this has 3 sig figs, so our answer needs to have 2. So 5,344 is going to be rounded to 5,340. Or excuse me, 5,300. Let's look at heat of vaporization example. How many joules does it take to boil a 250-gram sample of water at 100 degrees Celsius? So again, this is a heat of vaporization problem, so let's list out our variables. And in this case, we're going to use the other constant, this 2260 constant instead, because we're talking about heats of vaporization. So we're going to plug it into our formula, and then we're going to solve. And this has 3 sig figs, so does this, so our answer needs to have 3 sig figs, so we're done. So let's look at this practice problem. It says, how much heat is needed to melt ice at 0 degrees Celsius if the sample weighs 255 grams? Pause the video, unpause when you're ready. Great, well, welcome back. What you should have figured out is that this is a heat of fusion problem because we're talking about ice melting, and on that plateau line, that is fusion. So list out your variables. You need to make sure that you use the right constant. So this is the heat of fusion constant, so it's the 334 joules per gram. Plug into your formula and solve. Again, 3 sig figs, 3 sig figs. We need 3 sig figs total. All right, let's look at this practice problem. Calculate the number of joules needed to vaporize 423 grams of water. So pause the video, unpause when you're ready. Great, what'd you come up with? Well, there's a clue in this question. It says vaporize, so you should have known that you needed the heat of vaporization. So you plugged into your formula, and you should have gotten your answer. We have 3 sig figs here, 3 sig figs here, so rounding this big number to 3 sig figs, we'll get 956,000. All right, let's look at this, check your understanding. We're going to start off with this tomorrow in class, and then we're also going to look at this one. The one thing you need to remember is that when you're looking at a heating curve, all of these different plateau pieces have different equations that go with them. So in your vertical parts, so the parts where your temperature increases, your average kinetic energy increases, but your potential energy is going to remain the same. On the horizontal part, your plateaus, the temperature is going to remain the same. The average kinetic energy is going to remain the same, but your potential energy is going to increase. So that's another way that we could assess and ask you questions about a heating curve. For a cooling curve, it's going to be the opposite because heat is going to be removed over time. So on your vertical parts, your temperature decreases and your average kinetic energy decreases, but your potential energy is going to remain the same. On your plateauing parts, your temperature remains the same, your kinetic energy remains the same, but your potential energy is going to decrease because you're going from objects that are going to have a lot of movement and a lot of energy to objects that are not going to have a lot of energy. So remember the 3 P's when you're going through this. Plateau is a phase change, and that means your potential energy is going to change. And on the diagonal parts, the temperature is changing, and therefore your kinetic energy is going to change. See you in class tomorrow.